So you're still in chapter 1 of Landau?
Finish chapter 1 and move into chapter 2. We'll do chapter 2 today.
Cool.
And
They Russian or German? Are they Russian?
oh yeah, Landau Ch1, yes, Russian. Russian during the bad old days, of course, where Landau was not allowed to travel outside Russia and all that sort of thing.
That's cool. I mean,
These were, these series of books were all translated, and yeah, there's many stories about Landau. So I find much of the presentation in the Goldstein in this first chapter to be kind of turgid, and so I think it's good to give you this alternative presentation. And I think I've spoken about this before, that there's always this argument about whether one should present things in the historical kind of recapitulation of the historical development of the field or not. And certainly Mr. Landau is the opposite of that. The book is a little bit more in that way of the coming about it as people uncovered these things approximately 200 years ago. Some of these brilliant folks were writing down some of these things just as the mathematics was being developed. Really pretty amazing how far they went in getting this all straightened out and laying the basis then for the development of E and M, which was coming along, but which didn't come along as fast. So at any rate, where I left off last time was okay, I was not quite finished with chapter 1 and have made the point. Well, we talked about you couldn't have negative masses, or then the Lagrangian trick doesn't work. The variation goes to minus infinity, so negative masses are forbidden. But that is in the mechanics, that negative masses are forbidden. The question of anti-gravity and so on in Newtonian theory and general relativity beyond that is another issue entirely. One we won't actually, the GR we won't actually come back to until, well, another course. Okay. So what we learned was that you could compose the Lagrangian, which we started out not knowing at all what in the world it was, but through these simple arguments we said it's a function of squares of velocities, and that you can add in a function which turns out to be the potential energy. So one thing you can write down, just a little trick, another sly Landau trick, is that since you can write down that v squared is equal to dl dt squared, you can write it in this way that our mathematician friends would hate, like this. And so we, since dl squared, the length element is in Cartesian coordinates equal to dx squared plus dy squared plus dz squared. We can write down that L is equal to 1/2 m x dot squared plus y dot squared plus z dot squared. Or we can write down in cylindrical coordinates dl squared is equal to dr squared. Gotta get new glasses. Plus r squared d phi squared. I got new glasses just earlier this fall. I think they must have screwed up the prescription because I can't see very well at all. And so the Lagrangian is equal to 1/2 m r dot squared plus r phi dot squared. Here it's squared. And z dot squared. And in spherical coordinates, the dl squared is equal to dr squared plus r squared d phi squared plus, d theta squared plus then the r squared sine squared theta d phi squared. And the L then is 1/2 m again, r dot squared plus r squared theta squared plus r squared phi dot squared sine squared theta. So there's not much to say except that, well, one thing, of course, is that when we start using other nasty coordinate systems, and you get these funny looking terms, of course, as you well know, and life gets more complicated. In fact, it's a bizarre and strange thing that we will come across as we go through the course of how much complexity in physics has to do with the fact that life is not simply in Cartesian coordinates, and that spherical symmetry, as in the hydrogen atom, for most prominent example, leads to all of these nasty spherical harmonic functions and so on, which doesn't seem like they ought to be that damn complicated, but they are. And that has to do deeply with geometry of space and all of these funny things of the things that you'll see in quantum mechanics, the peculiar relations amongst angular momenta and so on, all have to do with the geometry of a sphere. Quite strange and marvelous. At any rate, so for a system of particles, I'm going to get rid of this. For a system of particles, then we can write down the Lagrangian being equal to 1/2 ma squared, ma va squared, and the sum over the index a for the particles minus some function u of r1, r2, etc. Where those are the positions of the particles, but that so that the kinetic energy is just this term here. And we are making the assumption for all of this course until we get to the last chapter that whatever force persists between the different particles propagates them instantaneously. So for the moment, if we're considering just a closed system of particles, we can have all kinds of interactions between the particles, all possible combinations being added up in here.
What do you mean by closed system?
That's what I'm just getting around to saying.
Sorry.
A closed system, thank you, though. That I'm not including any interactions with something out here. So that this potential at this moment we're talking about including only the interactions between these particles. For example, if they have charges, or if they have gravitational attraction, or in the more messy circumstance, if they have the electromagnetic interactions. So, but we're adding this up for the classical mechanical case as though the motion of any one of these guys here is instantaneously transported to all the other particles, that there's no delay time. That, in other words, assuming that the speed of light is infinite. So you can see that life is going to become more complicated when we get around to eventually with Mr. Einstein saying that there is in fact a maximum velocity called c. In the same spirit of sneaky spirit of Mr. Landau, you can derive all of relativity from the one assumption that there is a maximum velocity. And it's the same in every system. And once you do that, then this is in trouble because the hidden assumption here is that the velocity of propagation of these forces and so on is infinite, and it's instantaneous, and which is, for most circumstances, good enough if you're calculating the orbits of planets and so on. Yes, the speed of light takes a little time to get between them, but they're not moving that fast. Certainly for talking about things here on Earth, most of the time it's plenty good enough assumption. But you can see how that's going to muck things up if we start putting in finite time delays into this.
I have a potentially stupid question, and it's mostly due to ignorance.
Usually the stupid questions are the dangerous ones.
Is there an upper limit on the propagation of gravity?
Experimentally?
Anything. I don't know.
No, generally people, one thinks, and it is a necessity in general relativity, that the propagation of gravity is at the speed of light, c, and there's only one c. Why is there only one c in the universe? That's a good question. But if there's not, as we had, you're going to get me down on this side. Last year there was, or 2 years ago this fall, there was an interesting fracas from CERN where people had found some evidence, they thought, from an experiment in the ground Sasso-ton, that neutrinos actually were traveling slightly faster than the speed of light. And this was really a great exercise because it set people off to thinking what would happen. And Jesus, it really lights a fire under practically all of our modern understanding of physics. And it was such a great exercise because it showed how stable Einsteinian understanding of things is, because just nobody came up with a decent theory. There were a lot of cuckoo things proposed and nothing really worked. And then it was found out that it was all a mistake due to a fiber optic connector in the ground Sasso tunnel experiment. So, yes, I chuckle. The fear of any experimental physicist, to go out there and make some great announcement that's going to get you the Nobel Prize, and then you find out, uh-oh. Okay, yeah. Right. So this has to do with the assumptions, the Galilean assumptions of the absoluteness of time, that there is a time that would apply to us and in people in Andromeda or wherever. It would all be, our clocks would all run perfectly simultaneously, which is not entirely true. So the space, and we keep using these several terms, that space and time, that time is both homogeneous and isotropic. So do you understand what those terms mean? Homogeneous means it's the same across space in different locations, and isotropic, that it doesn't depend on direction. So if I'm communicating with you over there versus over there, it doesn't make a difference. And moreover, right away we come across a fundamental principle of physics, and I should then give you a little context for this. Much of modern physics, people have, as we mentioned, Noether's theorem, these invariance principles and things that are conserved, that three particular principles, C, P, and T, have been very important to fundamental particle physics. And you will come across it in your quantum mechanics in particular, that physics is classically presumed to be invariant under C, which is changing everything from matter to antimatter, P, reflecting in a mirror, parity, and T, reversible in time. And while that's, for our purposes here, we don't care about C here, but P and T, that this T invariance that shows up in the Lagrangian is a statement that all of classical mechanics runs just as well forwards as backwards, which, if you're coming at it from another universe or something, might not be so obvious. But on the micro scale, all of mechanics is time reversible, has T invariance. Let's see, where did I want to go with this? Right, okay, so anyway, for knowing the Lagrangian, then we can write down d dt dl dVA, just one particle, is equal to dl dRA. And so that statement we get by just this argument of the T invariance of the equations, and therefore we write down that this is true, and immediately then we get MA is dV dA dt is equal to minus du dRA. And so that ought to look very familiar, because that's just good old F equals MA.
Yeah.
And so we call this the force. So we've come up with F equal MA's kind of smoke and mirrors, but we've come from these very general principles of homogeneity and isotropy of space and so on, and that the Lagrangian must depend at least on quadratic terms of the velocity. We wind up getting F equals MA. And we define a force thereby. We haven't said anything about our intuitive understanding of force. This is a definition of the force, not the force that is in the movies, but force that moves individual particles, and then we'll talk about ensembles of particles. Moreover, that since this depends only on the coordinates and their particles, then the same thing applies to an ensemble, and we can write this in a more general form so that if XA is equal to FA of some new set of coordinates Q1, Q2, however many, and XA dot then is equal to the sum of the FA dq sub k, q dot k, and so on. When we substitute those back in, we can then write the Lagrangian of this ensemble be equal to 1/2 the sum of MA x A dot squared plus Y A dot squared plus Z A dot squared minus U goes to equal 1/2 sum over I and J of A I K, K, I'm using the index K, it doesn't bloody matter, of Q, Q I dot Q K dot minus U of Q. So this is the interesting thing here, that in these generalized coordinates, that you get these funny cross terms in here. And the thing to notice that is that here the dimensions of these guys can be something weird as we transform to another set of coordinates. And that you do get these funny cross couplings. So we like, of course, systems where that becomes much more simple.
Professor Lerner?
Yeah.
So I'll do my classmates a favor and I'll be the village idiot, so I'll probably be asking all of the stupid questions, but what is
As I
Q?
say, it's always the stupid questions that are the dangerous ones.
What is the Q?
Oh, Q is an, yes, thank you.
It's a generalized
Q
coordinates?
is some generalized set of coordinates, right? Which we will define in many different ways as we go through different problems and so on, but a general set of coordinates. And we'll get around to fancier definitions later on when we talk about canonical coordinates and so on. But for the moment, you can think of them as writing in different coordinate system, or you can think about writing them as a description. Say we've got a car traveling along, and one coordinate describes the car, and another one describes the height of something riding on the car. An infinite number of different possibilities, but these are generalized coordinates. They don't have the dimensions of necessarily of length.
Got it.
So what is the difference? What's the difference between the two indices in that final line?
Nothing
I
at all.
and K, and you.
Nothing at all.
So K is the generalized coordinates describing.
It's just an index running over the set of these coordinates. So
Right, and I is the coordinates for which.
The same. It's just that it's the matrix. This AIK is some matrix of all of these 1, 1, A, 2, 1, A, 3, 1, so on, of this whole set of n by n.
And A is just more like a basic coefficient out in front, like a mass.
Right,
almost.
exactly. And it is, in fact, a generalized mass.
It's just to make things pretty.
It's 1/2 mass in the usual case. Well, it's not just to make things pretty.
But it's to make things work out.
Yes, yes. But we put the 1/2 in